Good morning, everyone. Lots of people in the chat saying good morning, and that's always a nice thing. It's always nice to increase the amount of niceness in the world. Anyway, kind of funny about the stream today. The audio sync is off by a second and a half. So, I don't know if that's going to hold for the whole stream because it seems kind of extreme. So if you guys notice that the audio sync is has somewhat normalized, or if the audio sync becomes off in some way during the stream, please just let me know in the chat and I'll fix it for you, because a second and a half is just a long time for the audio to be desynchronized. It would make the video just about unwatchable, in my opinion. So anyway, we should probably continue with what we were talking about last time with respect to all of the data structures that we now have access to. The correct way to think about data structures is to think of them as tools. That's the correct way to think about most of the things that you have available to you in terms of programming. For loops are a tool. Data structures are a tool. It's not that you can't... The interesting thing about computing is that you don't need any of these things to accomplish a task. All you need to do is, what I'm trying to say is, any of these constructs that we're talking about can be fully expressed in the simplest concepts that we talked about during the first lecture or so. The first lecture was mostly introduction. Say the second lecture. You can do all of this stuff with for loops and if statements. Because fundamentally, what the computer is doing is it's taking all of this stuff and compiling it down to that basic level. So if you wanted to, you could actually perform all of these functions at that basic level. The trick is that it takes a long time to do that. And if you have these more advanced concepts available to you, they can make it much easier to program. But the correct thing to do, the correct way to think about it is, a dictionary is a tool. In the same way that, if you're undoing a bolt, you can use a pair of pliers instead of a wrench. It won't work as well. It'll be harder and, less efficient, but you can do it. But, if the job calls for a wrench, use a wrench. So let's talk about some problem solving. Hopefully we'll get through this material today, and then we can start on the actual stuff we're supposed to be doing this week. So, computing change. Here's a problem formulation for you. Compute the smallest number of coins or bills that sums to the target amount. For example, our Canadian coins are 5, 10, 25, 100, and 200 cent coins. If our target amount is $1.85, our change would be 0 nickels, 1 dime, 3 quarters, 1 loonie, and no toonies. Yes, for those of you who are outside of Canada at this particular point in time, I know that we call our money funny names. But that's okay, because, that's one of our national idiosyncrasies. However, there's an important constraint on this problem. We want the smallest number of coins. It's entirely possible. Without that constraint, you would consider this to be an underdefined problem. So, if you were to think about it algebraically, the number of coins that you would want in each of these categories would be a variable, and we would have one equation with 5 variables. That's an underdefined problem, right? There's no algebraic way to come to a single solution. So, if you're trying to solve things algebraically, at that point you say, So the problem has no solution, or the problem has many solutions. What you could do is you could rearrange the equations to find some of the variables in terms of other variables. That's typically what we do. And then we would specify the problem saying something like, given, we know that this solution contains X number of nickels, how many dimes would you need, and that sort of thing. But right here, this constraint that we want to find the solution that contains the smallest number of coins or bills, that provides us enough information to be able to come to a single determinate solution. The only problem, of course, is this property, smallest number, minimize the number of coins or bills, that's somewhat more difficult to express algebraically. You might think of it as minimizing a function in terms of calculus, but even then, there are so many variables in this particular problem that it's difficult for algebraic analysis. And at this point in time, if I had my chalkboard, I would write the algebraic equation for this on the chalkboard, but since I don't, I guess I'll just write it in my handy-dandy text editor. So it would be something like 185 is equal to x times 5 plus, or 5x plus 10y, or I should start lower, shouldn't I? uxw10 plus 25x plus 100y plus 200z. Basically, the question is, in algebraic terms, solve for u, w, x, y, and z such that the sum u plus w plus x plus y plus z is minimized. Cool. Okay, yeah, okay. I'll do an audio resynchronization test. Okay. The audio has gone its own way. Gone its own way. See, I knew that a second and a half was too much, that it would resync at some point. Still off. Guys, sorry about this. Just give me a moment. It's kind of unavoidable. Did I miss it? Did I miss the test? What a pain. Okay, if there are any mods in the chat right now, if you guys wouldn't mind cleaning things up a little bit, then that would be wonderful. Seems we've attracted some attention. So cool. All right. Anyway, let's go back to where we were talking. All right. So anyway, we were talking about the this coin solving problem. So while this is a difficult problem to solve algebraically, well, it's also a reasonably difficult problem to solve algorithmically, but for different reasons that we'll see. Different but related reasons. But let's try to come up with a solution to this problem that's an algorithmic solution, and then we can worry about whether or not it's the correct answer. So, in order to formulate the problem algorithmically, we need to know what the inputs are and what the outputs are. So, let's say that one of our inputs is a tuple that contains all of our coin denominations as integers. So this right here, this information would be collected as a tuple. Our target value would also be an input expressed as a tuple. Or, sorry, not as a tuple, as an integer. Ha! As an integer. So, in this case, with respect to a Python function, we would have the first one as a tuple. We would call that coins, and we would say target is the second one. So, what's our output then? Well, we are primarily concerned with what the values of u, w, x, y, and z are. So, that would be what we need to know, so that's the output. The question is, how do we express that output? Well, let's make use of some of these data structures that we have recently discovered the existence of. So, since we are relating a coin value to a coin quantity, it makes sense for this to be a dictionary. So, our output is going to be a dictionary. So, generally speaking, the methodology that is most intuitive is to find how many coins, how many of the largest coin you need, shall we say. Let me rephrase that. Consider the largest coin denomination, and consider how many of that largest coin will fit inside of the total that you now have. You then reduce the total by that number of coins, the value of that number of coins, and then you take that subtotal, pass it down to the next coin denomination. So, in this particular case, if we have 185 as our target amount, there's no there's no toonies that'll fit inside that, so we don't want any. So Z would be 0. For a loonie, for 100, we have one coin that'll fit inside that. So we would say y is equal to 1. I'll just keep the tally of this. Y would be equal to 1. Our new target, it will be 85. We then examine the 25-cent coin. If we make the 25-cent, if we consider the 25-cent coin, 3 of those will fit inside of 85 with 10 remaining. It's essentially a division problem, right? So our target will then become 10, and we will have oh, that should be x, pardon me. We will have 3 quarters. W represents the number of dimes. Since the target amount is, 1, with the target amount is equal to the value of 1 dime, we would have 1 dime as the resulting coinage. And, since there's nothing left, we would have no nickels. So that's one way of going about finding a solution to this problem. It's not a bad solution, although it does have some flaws, as we'll see. But let's see what that looks like in Python. So our coins are a tuple, right? So what we want to do fundamentally is we want to for loop over each of the values in the tuple. So just for the sake of making the algorithm a bit simpler, let's imagine that our coins are in descending order. If they're in descending order, then when we for loop over them, we will end up with the largest value first, which conforms to this idea of how to compute this algorithm, compute these coin values, or coin quantities, shall I say. So we'll just make a note of that. Coins is in descending order. Of course, if you don't want to assume that coins is in descending order, then you can always do something like coins.sort. Well, it doesn't work on tuples, but if it were a list, you could do this, and then you could just reverse it, and that would sort the coins and put them in descending order, because sort puts things in ascending order. But we're going to assume that they're that way. So for C in coins, we want to take our target value and see how many of our coin target value, or the current coin denomination that we're working with, how many of those fit inside our target value. Another way of saying this is the division, right? And we're doing integer division here. So number of coins is equal to the target integer divided by, remember integer division is a double slash operation, divided by the current C value. So that's the number of coins that'll fit. We want to save that into a dictionary. So let's initialize one. Dictionary is equal to an empty dictionary. We can add the values as we add them, or as we generate them. So dictionary at C, because we want to relate coin denominations to the numbers, is equal to num. So that's good. That stores how many coins fit inside the target value. However, we want to modify the target value now so that on the next loop iteration, that target value will reflect the decreasing amount that we have left to compute. So target is equal to target modulus C. Remember that modulus is the remainder of integer division. So because the target is the remainder, this is the natural operation to be performing on it. Then, of course, we wish to return our dictionary. There we go. Cool. Let me just check to see how chat is going. Cool. So, yeah, to clarify, this C here takes on the value of each element of the coin's tuple in order. So, on the first loop iteration, it's the first value in coins. On the second loop iteration, it's the second value in coins, etc., 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 all the way until it runs out of values in that tuple. Yeah. So, could I go through the whole loop which the values are done after I'm done with the function? Yeah, so we can run this. We can actually run this and print out what the values are as we generate them. So let's add some print statements and actually run this so that we can see what the behavior of the algorithm is. Because I think this is the first example of us going through something to this degree of depth. So, print, we will want to print the dictionary itself. We will wish to print what the target is, so target equals plus string convert target. We will wish to say print number of coins is equal to string convert num, and print dictionary so far plus string convert the dictionary. Usually this works pretty well. So let's take this, and I'm just going to comment all this. Oop, that's the wrong comments! Oh my gosh, I'm using C-style comments. I tell you, when you're teaching two classes, and they're both using different styles of comments, it's like, man, good luck keeping it straight. It's terrible. Okay, there we go. So this now makes that a valid C file. Let me just save this somewhere quick. Boom. Do-do-ba-doo. Code. Sounds good. We'll call this coins.py. So let me just open up that. There we go. Let's open this up in the terminal, and we can execute it. Python 3 coins.py. There we go. It doesn't print anything. Oh, right, because classic example of a typical Python error. Although we have defined the function, we've never actually invoked it. So you actually have to pick some values and actually invoke the function. Make change. So let's use the example that we were using in the slides. 200, 100, 25, 10, 5. There we go. So, on each subsequent iteration of the this is called tracing. So this shows you what the function is doing on how the variables are changing as the loop loops through. Actually, you know what? Let's add C in there just to make things super crystal clear. There we go. So, on our first round, C is equal to 200. Our target was 185. Now, keep in mind this is printing out after. Yeah, I should probably put it at the beginning, eh? Not much good. Otherwise, there'll be a mismatch in, you know. Oop, unbound local error. Num equals 0. I think that'll help. There we go. So, for the C equals 200, okay. Huh. Let's move that. So, target and C can be considered the inputs to this part of the algorithm, and the number of coins in the dictionary thus far can be considered the outputs to like this subsection of the algorithm. So it makes sense to look at what our outputs are after they've been computed on each loop iteration. That's, there we go. So when C is equal to 200 and the target is equal to 180, the number of coins is 0 and the dictionary so far is 200, 0. When it's 100, our target is 185, number of coins is 1, and you see that gets entered into the dictionary. The same goes for the quarter and the dime and the nickel. So that's how our data changes as the program is executed, which is cool. There we go. So that's how you would write a version of this algorithm. Now, the interesting thing about this, and I know the thing I'm kind of doing right now is I'm going through several slides. We'll catch up with the slides in a bit, but here's an interesting thing, right? What if we altered the coin values? And I know these aren't coins that actually exist, but let's imagine that we had a particular let's say we wanted to compute 15 cents, and we had a 7, yeah, okay. All right, yeah, okay, I'll use the slides. I'm trying to remember from memory what the coin denominations are that break this algorithm, and I can't. Well, there you go. Anyway, so again, the general procedure we used was to take out as many of the biggest coin as we can until we can't take out any more. Take out as many of the next biggest coin until you can't take out any more, etc., 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 and record how many of each coin we took out. That's the purpose of the dictionary. So this is an example of something called a greedy algorithm. Greedy algorithms are a solution to this type of problem, but they're not the only solution to this type of problem. The reason that we call it the greedy algorithm is because on each iteration through the loop, each coin denomination is taking as much out of the target value as it can before it moves to the next one. This does not guarantee an optimal solution, but it will arrive at a solution. So here is, in the slides, some version of the thing that we just did. Notice that they've reversed the, versus our implementation, the arguments are reversed. That's not a huge issue. Obviously, we also have more print statements. And notice also they're using a while loop here rather than using a for loop. Because they're using a while loop, there are a couple of extra lines that don't need to exist. 3 extra lines in this solution versus ours, if you don't count the print statements. This is like normally like the number of lines in a solution isn't the most important thing about a solution. The most important thing about a solution is whether it works. But, some people like to optimize for fewer lines of code, and I can respect that. So, here's the question. Will our greedy algorithm always give the smallest number of coins? Well, I've already said several times that it's not guaranteed to. So, here's an idea. What if our target amount was 14 and the coin set was 1, 5, 7, and 10? So, that would be 10, 7, 5, and 1, and our target was 14. Let's see what this does. So you can see it's taken 1 dime and 4 pennies. Now, if we're trying to minimize for the number of coins, obviously the minimal solution to this one would be to take 2 7-cent coins. So that's, So the greedy algorithm that we've laid out does not give us the correct solution. Or it doesn't give us the most optimal solution. And since we've defined correctness in this case to mean the most optimal, like the optimized number of coins, that makes it incorrect considering our interpretation of the problem itself. So this will happen, well, this has the potential to happen whenever you have coin values that are not at least twice the value of the previous coin. So in this case, a 5, twice going backwards with respect to us. 5 is, of course, 5 times 1, but 7 is less than double 5, right? And 10 is less than double 7. So this introduces the preconditions for the greedy algorithm not arriving at the optimal solution. So generally speaking, and this is kind of a rough introduction to the idea of algorithmic complexity. There are some problems that are easy to solve with algorithms and some that are hard to solve with algorithms. In order for this algorithm to be able to compute the correct number of coins for this particular set of coins, in order for it to have found the 2 7-cent piece solution, you would need to employ backtracking or some sort of similar strategy. You would need the ability for the problem to look back at the previous coins that it had calculated and decide whether they're optimal or not. Now, because this is a greedy algorithm, it's incapable of doing that. Once it has computed the value of one coin, the number of one particular denomination of coin that it's using in this particular solution, that's it. It does not revisit that information. It considers that to be the correct value with respect to the solution. So in order to have found this 2 7-cent piece solution, you would have to have an algorithm that would essentially establish 10 as being 10-cent piece as being a provisional solution and re-examine that solution based on the values of coins later down the line. There are some algorithmic approaches to this type of problem called dynamic programming, which you probably won't study until second-year algorithms, when you take second-year algorithms. But that type of algorithm, generally speaking, you have to take a hit in runtime to be able to produce that type of a solution. So, generally speaking, the solution that we've written here is what we call a polynomial time solution, because the equation that relates the amount of time it takes for this piece of code to execute to the number of inputs can be represented mathematically as a polynomial. So, ax squared plus bx plus c, something like this. In this particular one, because it's only got one nested loop, that will be the complexity would be proportional to n, not n squared. But, this is kind of getting into stuff that, this is stuff that you, don't worry, this stuff isn't going to be on the test. Once you start getting into the generalized solution to the make-change problem, it is the algorithm which performs that, because it's got looking back at its own solutions, it is a non-polynomial solution. So generally speaking, this means the solution is somewhere in the neighborhood of 2 to the n instead of n squared, right? Big difference between those two. So this is like your rough introduction to the idea of NP-hard problems. This is an NP-hard problem, a non-polynomial hard problem. Generally speaking, in the field of computer science, if there was a solution to make non-polynomial hard problems into polynomial solutions, you would have this dramatic, sudden leap forward in computational strength, and many problems that are considered intractable now would be easily solved by computers, and it would probably also break all existing encryption. But generally, the general feeling among computer scientists with respect to the problem of P equals NP is that the solution to P equals NP is some sort of mythical El Dorado or Holy Grail. It's some sort of magic MacGuffin that may not actually exist. It might exist. The tantalizing thing about P equals NP is that there's no proof that it doesn't exist, which is an interesting thing to think about, that there can be proof that things don't exist, but there's no proof that P equals NP, the solution to that, doesn't exist somewhere. We just haven't found it. But the prevailing attitude is one of skepticism, shall we say. So that actually rounds out our topic 4 slides. I'll just see what's going on in the chat. Yeah, just factor out the P. Yeah, that's awesome. Great analogy. Big difference between bringing up the existence of a millennium problem and actually solving one. But there we go. Oh, good question. So what is the purpose of string C? So this is actually implicit in the print function, and also when it displays things to the display, or displays things to the terminal. But if you wish to blend strings with other data types, you can't just do that. That's a type error, right? But if you convert it to a string, then it works. So all it does is it just takes the characters and it encapsulates them inside of a string. It's just a way to make things work. But yeah. Question: how deep do we go into algorithms in this class? Not especially deep, but it's important. I think we sort of hit peak algorithm while we're talking about recursion, which is actually the next set of lecture slides. But ooh, that's 2MP3. Yeah, no, we're not gonna get, like, algorithms is a very, very deep well, and you can spend your entire life studying algorithms and not get to the bottom of it, which, is true of a lot of academic disciplines. But at some point we're going to talk about big O notation and sort of establish some of the framework for, rigorous thinking about algorithm structure. We're going to talk about that to a certain degree in the when we start talking about our next topic, which is all about functions and recursion. But yeah. From my perspective, we're only going to scratch the surface of algorithms. But yeah. So that's a good question. What's the difference between double slash and slash? So double slash is integer division, and single slash is floating point division. So if we have 10 divided by 4, that's 2.5. If you integer divide it by 4, you get 2. So it's like long division. You have, 10 divided by 4 is 2 remainder 2. Double slash is the 2, and modulus is the remainder 2. I know that doesn't show up particularly well with 10 and 4 because it, they're both the same value, but yeah. There we go. Cool. Don't feed the trolls, guys. Yeah, I guess we're gonna have to move back to unlisted videos for a little while. Wait for things to cool down a bit. So, although, thank you very much for moderators for staying on top of those sorts of things. Don't be afraid to just hide people completely instead of just banning or just hiding single things they say. Cool. All right. So, we've got about 8 minutes, which is enough time to at least start topic 5, which is good. No, I don't want to open in Firefox. Get out of here. Get out of here with that stuff. There we go. So, functions and recursion. So, we've talked about recursion. We gave shall we say, a rough introduction to the concept of recursion. As you can see from the outline of the topics, we are definitely spending a significant portion of time discussing recursion in this particular set of slides. So, let's get to it. Functions. So we've been using functions. You guys have been using functions in the assignments and the test so far. Functions are a mechanism of abstraction. It allows you to take a subprogram and refer to it by a single name. Of course, you have to specify the inputs and outputs, but that's good. That's a structured way of, it's a structured way of abstraction. It's a structured abstraction mechanism, which is good. We like structured abstraction mechanisms. So functions are a way of grouping together a sequence of operations under a common name so we can refer to it multiple times later. In concept, they're similar to mathematical functions such as cosine, exponentiation, logarithms, etc., etc., etc. However, it really is the correct way to think about it, to think of a function as a subprogram. Just to remind you of the syntax, not that you really need it, we start functions with the def keyword, then we have the name of the function, the list of the inputs, a number of statements which compose the body of the function, and then at some point in the function we need to return a value back to the program which invoked the function, or you don't. It's optional. In Python, it's optional. Oh, and there are all the little boxes. So, this is an important point with respect to nomenclature. When you define a function, the names that the arguments to the function are defined as, these are called the formal parameters. So, the inputs to a function, you'll probably hear me use several different terms for them, because they're called different things in different languages. In Python, they call them parameters. In other languages, you call them arguments. So you'll often hear me mess up and call them arguments rather than parameters. But there's a difference between these, which are the formal parameters, and these, which are the actual parameters. So the formal parameters are those which are used within the context of the definition of the function. So this is the function's definition, and the inputs used inside of them, those are called the formal parameters. When you are providing actual values to the function, these are called the actual parameters. They are actual because these are the values that are being actualized. These are the ones that are being used to actually perform calculation. The formal parameters are not executed unless they are being given values through the process of providing actual parameters. So, there you go. This is called function invocation, by the way. Although, again, there are a couple of words for it. You'll often hear me use the term invocation because I like the word invocation. It rolls off the tongue. But the sort of more common way to say is that this program is calling this function. So a function call and a function invocation are the same thing. So here's an interesting thing. In Python, it is possible for you to define a function in such a manner that a parameter can assume a default value if nothing has been provided to it. So if we go back to our coins example from previously, if we make it has to be applied to whatever the last argument is in the list of arguments. But if you put an equal sign and then some value, for example, our default coin arrangement, 25, 10, 5, if no actual parameter is provided to the function call, then this parameter will take this value when it executes the function. So it has a default. So if we, just to illustrate that, if we now compile this program, or execute this script, you notice that although the parameter has not been provided, which provides the tuple of coin values, these ones are still being used, right here and here, because, we set a default. Setting default parameters is a thing that I occasionally, there's probably going to be at least one test question at some point in this course, either on the tests or the exams, where you'll be required to know what a default parameter is, and fortunately it's not that difficult. Lots of things, these are also sometimes called optional parameters, because you have the option of whether to provide them or not. Yes. Just be careful you don't get confused when there are multiple optional values. The interesting thing about that, actually, when there are multiple optional parameters, there's a special way of addressing them. So if we take a look at the print function, which we all know and love, you'll notice that this is the actual definition of the print function. There are a whole bunch of these optional parameters. Most interestingly, an end of string character. So in this case, the default value for that is the new line character. So when you print something, it puts it on a new line, right? It automatically presses enter. That's another way of thinking of it. However, if you wish to make the end of line something else, like we're talking on walkie-talkies, you'll notice the new line isn't actually added. Instead, what we specified is added. However, if you go by the order in which the arguments appear, it would be you have to specify quite a few things before you get to end. That's why it's allowed for you to specify which parameter you're assigning this value to inside of the function as a function parameter itself. So you can pick which one you want to provide a value to by having putting that name, an equal sign, and then whatever value you want to give it. That's a useful thing to know. And that's our time, actually. So I'll stay on the stream for a little bit. I don't have much time because I have another class that I need to do. But yep, that's it for today. I'll just take a look. Lots of people are asking, are having lots of questions about stuff. Most people are talking about Haskell, but sometimes, need more mods? Okay. Okay. I've seen you a lot. You can be a mod. Now we have 2 mods. Cool. Right. Doesn't seem like there's any questions. So if you guys have any questions, put them up, throw them up on Piazza, and that'll do. And incidentally, I think we're gonna take some stronger measures about. Sorry, Rimby isn't around at the moment. Anyway, take her easy, folks. I'll see you on Thursday.